Hi dear students, how are you all? Myself Sunil Mishra, and today I'm going to teach you one of the most interesting chapter of grade 9 mathematics, that is chapter number 10, circles. So without much ado, let's roll into the session. Imagine that your car has square wheels. How fantastic that ride would be. That will be a very bumpy ride, isn't it? So you have come across many objects in your day-to-day life that are round in shape, like chapati you eat to get energy, wheel of your car, dial of clock, keyring, button of shirt, bangle, and the coin you need to buy toffees. All these objects are circle in shape. In this chapter, I'm going to teach you circles, some important terms which are related to circles, and interesting properties that you use to solve tricky questions of circles. So without much ado, let's dive into the session. Okay, let's understand the basic definition of circle. Circle is a collection of infinite points on a two-dimensional plane, which are at a fixed distance from a fixed point. So this is the fixed point, and the distance of all these points from this fixed point is same, and this distance is called the radius of the circle, and this fixed point is called the center of the circle. I hope this is clear to everyone. It is very simple. So circle is a collection of points which are at a constant distance from a fixed point. The fixed point is called the center, and the fixed distance is called the radius of the circle. Now let's understand what is circumference of a circle. Circumference, or the perimeter of the circle, is the length of total boundary of the circle. Let's suppose if you move along the boundary of a circle and complete one rotation. So distance covered in this one rotation is equal to its circumference. Now let's understand what is chord. So chord is a line segment that connects any 2 points on the circle. So we have 2 points R and S on the boundary of circle, and a line segment that join RS is called chord. We have one more chord, PQ. Now we have one chord that passes from the center of the circle, and this is chord AB, and it is passing from the point O, which is the center of the circle. So this chord is a spatial chord, and it is called diameter of a circle. And this diameter is twice of radius. The length of this diameter is twice of radius. Now let's understand about secant. So secant is a line that intersect or touches the circle at exactly 2 points. We can say secant is an extended version of chord. We can extend both the ends of chord and we'll get a secant. So chord is basically a line segment that starts from a circle and ends on a circle, but secant is a line. Now let's understand about arc. So arc is a continuous piece of a circle. So this is arc AB. This arc is called minor arc. Why? Because this arc is less than semicircle. So what is semicircle? So a diameter divides a circle into semicircles, two equal portions. So these two equal arcs is called semicircle. So an arc whose length is less than semicircle is called minor arc. And an arc whose length is more than semicircle, that arc is major arc. So this red color arc is called major arc. Let's understand a new concept, that is central angle. So the angle subtended by the arc at the center of the circle is called central angle. If we extend the end point of this arc to the center of the circle, so these are radii. So amount of turning or rotation between these two radii is the angle theta. And this theta is subtending by the arc AB at the center of the circle. So this is central angle, and if this theta is 180°, then the arc is called a semicircle. Now I will explain you about the segment of a circle. A chord divides a circular region in two parts, and these parts are called major segment and minor segment. Minor segment is a region which is bounded by minor arc and the chord. The region or the area which is bounded by chord and the minor arc is called minor segment. So the region which is present inside this yellow color boundary is called minor segment. And what is major segment? So major segment is a region bounded by major arc and the chord. So this red color portion is the major segment. Now understand sector of a circle. So sector is a region of a circle which is bounded by an arc and two bonding radii. So let me explain you. So this is minor arc ACB and these are two bonding radii. So the region which is present inside this yellow color boundary is minor sector. And what about major sector? So major sector is the region which is bounded by major arc. This blue color arc is major arc and these are two bonding radii. So the region which is present inside this blue color boundary is the area of major sector. So let's start the first theorem of this chapter, and this is theorem 10.1. It says that equal chord of a circle subtend equal angle at the center. That means if two chords are equal, then they will subtend equal angle at the center of the circle. That means their center angles are equal. So let's prove this theorem. In this theorem, we have given that AB is equal to CD, and we need to prove that angle AOB is equal to angle COD. So let's start proof this theorem. So what we need to prove? We need to prove that angle AOB is equal to angle COD. And what is given in the question? It is given that AB, chord AB is equal to chord CD. So let's start the proving this theorem. So we'll take triangle AOB. In triangle AOB and triangle COD, in these two triangles, AO is equal to OD because these are the radii of same circle. So they will be equal. In the same way, BO will be equal to CO. Again, same reason, these are the radii of two same circle, and AB is equal to CD because it is given the question that these chords are equal. So it is given. So by triple S congruency rule, these two triangles are congruent. Triangle AOB is congruent to triangle COD. If these two triangles are congruent, then their corresponding parts are equal. That means angle AOB is equal to angle COD. So hence we have proved that if we have equal chords, then they will subtend equal angle at the center. Now let's start theorem 10.2, and it is the converse of the previous theorem. It says that if the angle subtended by the chord of a circle at the center are equal, then the chords are equal. So it says that if angle AOB is equal to angle COD, if these central angles are equal, then in that case the length of chords are equal. So this is basically converse of the previous theorem. So let's start proving this theorem. So in this theorem we need to prove that the length of chord AB is equal to CD. And what is given in the question? It is given that angle AOB is equal to angle COD. These central angles are equal. Now we'll prove this theorem. So for that we will take triangle AOB and triangle AOB and triangle COD. So in these two triangles, AO is equal to OD. Why? Because these are the radii of same circle. And in the same way, BO is equal to CO. Same reason, these are the radii of same circle, so they will be equal. And angle AOB is equal to angle COD. So this is given in the question. We have used here side in between angle and then side. Side in between angle and side. So by side angle side congruency rule, these two triangles are congruent. Triangle AOB is congruent to triangle COD. And if these two triangles are congruent, then we can say that AB is equal to CD by CPCT, corresponding parts of congruent triangle. I hope this is clear to you.